Well, until recently, it's been fashionable to say that the microcomputers coming on the market were only really for playing games, and that most people would never find serious uses for them. Well, over the next 10 programmes, we'll be seeing just what can be done with micros and looking at the principles of how you can use them yourself. That's why we're calling this series Making the Most of the Micro. Richard Gom suffers from cerebral palsy. He can't speak, he can't walk, his limb movements are unpredictable, but he can control the movement of his head. His disabilities, though, haven't prevented him pursuing an academic career. He's studying for a PhD in philosophy at Swansea. And it was the agony of writing long philosophical dissertations using an ordinary electric typewriter that first led him to consider how a computer could help him.
To me, huh? I'll show him who's all wet. It's just you and your Uncle Popeye.
The micro has opened up a whole new world for Richard Gom. He's now writing software to help other disabled people extend their abilities through computers. And he also claims to have discovered one of the most important laws in computing, Gom's law. Well, Richard Gom isn't the first to discover that computers aren't quite as foolproof as the adverts promise. But through that film, we've already seen a few of the jobs they can do, and jobs that are increasing in variety all the time. Now, you may have a machine of your own, or you may be thinking of buying one. And there's a confusing array of them, and the adverts are full of technical jargon, which we hope to explain. Well, although they're all similar, there are many small differences between machines, and we can't look at every one in detail, so for much of the time, we'll be using the BBC Micro. Well, with me today is John Coll, who wrote the user's guide to this machine and knows much more about it than I do. John, this is a fairly simple layout, but it's fairly standard for most micros.
That's right. It's got the three elements that you expect to find. The computer itself, a colour monitor so that we can look at the output pictures from the computer, and a cassette recorder for playing the programs back into the computer.
Well, I haven't got a monitor. I use an ordinary television set. What's the difference?
Well, that's fine. You can use that quite well, but with a colour monitor you get a much sharper and crisper picture, particularly when you're using colour graphics. It shows things up a lot more clearly.
But you can't use it to get television pictures, I suppose.
That's right, that's right. Now, both of those, the television and the colour monitor, plug in at the back. And in fact, that's where the ordinary domestic television set plugs in. The black and white monitor can go in there, and the colour monitor plugs into that socket. The next socket along here is used for plugging a printer in, or you can plug in a connection to a telephone line so that you can connect to satellite circuits and so on. An ordinary domestic cassette recorder plugs in there so that you can load programs. Then there are a few more up here. This socket is where you plug in games paddles, things like that. And these two at the end are special connections so that we can connect the studio equipment in and get a television picture from the computer.
Well, apart from those last two, most of the other ones are fairly standard. You find in most micros.
Absolutely. Very normal indeed.
Right.
Yeah. Well, let's load a program in. We've got a cassette here, an ordinary audio cassette, and we can load the program that's stored on there into the computer. So we type load demo 1 and press the return key, and then start the recorder playing. And in a moment, that will start a program loading from the cassette recorder into the computer. In fact, it's just started now.
What's the significance of those numbers?
Well, those numbers are rather like pages in a book. We're on page 3 at the moment, and each page has got a certain number of characters stored on it, about 250 characters on each page. The program is in fact stored as a set of audio tones or whistles. We can listen to those if we pull out this plug.
I always feel confident listening to that because it makes sure it's working, something's happening.
That's right, you can actually hear it. You may have heard just two different notes, a high note and a low note. Anyway, the program's just about loaded in. It's actually about 4,000 characters long.
It took about 20, 30 seconds or so.
That's right. It's not too bad, but cassettes are slow.
Yeah, there it goes.
Anyway, it's loaded in. Let's run it now. RUN, return. And this program is in fact a simulation of the loading process, of loading a cassette tape as it goes past the playback head on the cassette recorder. And I can start the tape moving, and you can hear the two notes that represent the 0 and the 1 that the computer understands. The high note represents a 1, and the low note represents a 0.
Well, as you said, this is a very slow method of getting stuff into a computer, but it is very, very cheap. Why not? Let's use a disk unit.
That's right, that's a lot faster. We've got here a floppy disk, and it consists of a piece of plastic, rather like the tape used on a cassette. It's inside an envelope, and you have to be careful to protect it. You mustn't scratch that surface, as you have to look after cassettes as well. And that is played through a disk unit. So let's plug that disk unit in. Got two connections. That first one is the power supply to the disk drive, and the second one is the data lead, or the lead down which the characters come. There, that's plugged in. And we can now plug the floppy disk, or insert the floppy disk into the drive, and we can have a look and see what programs we've got stored on this drive. Ask for a catalogue of the drive. See, there are lots of programs stored.
No, it's the whole list of them here, yes.
That's right. Well, let's take one of those and load it in. Load program called Demo 2. Just watch how quick this is. Go. to write.
Again, you could just hear it almost instantaneously. Well, how much faster is it than the cassette?
Well, it's about 100 times faster loading from floppy disk than loading from cassette.
And how much does it cost in comparison?
Well, the comparison is about 7 times more expensive for the drive unit than for an ordinary cassette recorder, but a lot faster. Let's run that program. And as you can see, it generates some high-res colour graphics and some music to go with it.
It's very beautiful. Oh, it's lovely. But to make this into a really complete system, what we need is a printer on it.
That's right. That's certainly the next thing to add on to the system. And we can plug that in again underneath.
And that you'd find on any other micro, you'd always find it.
Yes,
printer
indeed.
socket, yeah.
Somewhere to plug a printer in. Now, you'd want a printer really for 2 reasons. Either because you're developing your own programs and you want to be able to list them out, see what program instructions you've given, or else if you're using the computer as a word processor, you might want to print the letter out after you've written it.
A word processor that really converts into a rather sophisticated typewriter, enables you to correct errors or move paragraphs around without having to retype the whole letter.
That's right, that's right. And the word processor chip itself, or the word processor, isn't held on cassette or on floppy disk, but we've actually got the word processing program on this integrated circuit, this chip.
And that's plugged into the machine, into a socket in the
That's
machine.
right, we've got one inside like that. And by pushing that key there, we can enable that chip, turn that chip on, and turn it into a word processor. So let's now print out the script of this program. And the script is actually stored on floppy disk. So I'll tell it to print the script out. And you'll see in a moment that's coming from the floppy disk and appearing on the screen. At the same time, also on the printer over here.
Well, thank you very much, John. Well, different computers may appear to be very different, but deep down, the way the various parts are organised is very much the same with all machines. And it's been like that ever since the earliest computers. And if you look hard enough, some of those old machines are still around. When I think of the design of aircraft, I think of aerodynamics and complex mathematics, particularly in the design of the wing, which is, after all, what keeps the aeroplane in the air. But on a sailing boat, the sails are effectively the wing stuck vertically in the air, and that's what enables the boat to sail against the wind itself. But those sails, they're complex, they're three-dimensional, they're curved in every direction. A flat sail would have the aerodynamics of a brick. Being so complex in their shape, they require very complex mathematics to enable the optimum shape and the optimal design to be made, particularly for professional sails that consistently win races. This is a sail loft at Bruce Banks Sails, one of the largest in the country. It's here that the cut pieces of cloth are laid out before being sewn. You can see the subtle curves on these 2 pieces, which are about to be joined together to an accuracy the thickness of a pencil line. And that means very precise calculations. Up to a year ago, those sails were designed using this computer, a rare piece of antiquity. It's only 20 years old, built in the late 50s. But today, they're being designed on this micro. Not only is it a lot smaller, but it's much more flexible and even more powerful than this machine here. But looking at it, we can see some fundamental similarities. Similarities that exist on almost every type of computer you look at. They're overcoming the same types of problems, the problems of how to get data in. On this, it's done with a keyboard, and the output is either on a screen here or on the line printer. The little box here holds the memory and also the processor. It's very, very small. And the backing store is on a floppy disk, or a couple of floppies here, each one of these floppies holding 500,000 characters. And of course, it can be backed up by the old familiar cassette system. But let's look at how they solved the same sort of problems 20 years ago. Well, first of all, the data was input on punch paper tape, rather like this. It was produced on a typewriter-like device, punched the paper tape out, and then read on this reader here. This is the control panel of this computer, and commands can be issued by setting switches or even just dialing them through on this telephone dial. This is rather an interesting device. It's a meter which gives percentage program efficiency, whatever that may be. Well, once the computer's calculated its results, they can be output on this punch, once again, in punch paper tape form. But that's rather difficult to read, so in its turn, it's input into a teleprinter where the ordinary printout comes out. Well, that's the input, that's the output. The most fascinating part of this computer is this. The central processing unit and the backing store. Well, as you can see, it's a valve computer. It's a digital computer. That means it operates in binary. The numbers are carried in binary notation. In other words, a series of ons and offs. The backing store of this machine is this. It's a magnetic drum. It's rotating around here at 6,000 revs a minute, and on that drum is recorded the binary notation, binary numbers, and it's read off by these read heads here, one on each track. But how does information get from the paper tape reader, where it's read in, through this complicated maze of wires and so on, onto the drum and then be calculated on to eventually end up on the punch? Well, the secret is this. A gate. And this is a gate or a type of switch. It can either be open or closed, on or off. Again, binary positioning. And you can understand clearly how it works from this model of an AND gate. The signal will pass along this wire if that switch and that switch are both on. The alternate type of switch, there's 3 or 4 different types of switch in this machine, but this is another one, is an OR gate, which means that the signal will pass if that switch or that switch is switched on. Well, there are 500 or 600 switches in this machine to make it work. It's a beautiful mechanism. It actually still works, and the owners are looking for a good home for it because it's been replaced by this. The central processing unit from the micro they're now using, and unbelievably, it's got several thousand of those gates in it. Well, imagine yourself inside a microcomputer. You see arrays of chips and other rather mysterious-looking components. But where does the program from the cassette tape go when we run it into the computer? Remember the stream of musical notes, either high or low, correspond to our ons and offs. We call this a bit stream. Each of the beeps represents one bit of information. And because each bit follows the one before, it's called a serial bit stream. Now, somewhere over there is an area of the computer whose job it is to communicate with the outside world. There are inputs from cassette, disc, joysticks and so on, and chips to process the information received. The musical notes are converted into simple electrical ons and offs. This stream of bits then goes into another chip where it's packaged into chunks of 8, something like this. Each chunk of 8 bits is called a byte, and the program then travels 1 byte at a time as a parallel bit stream along 8 wires known as a bus into this thing that I'm sitting on. This is the main chip, if you like, the microprocessor, the central processing unit, or CPU for short. Now, because the CPU can handle 8 bits in parallel at once, it's called an 8-bit micro. Other CPUs can handle 16 or even 32 bits, but most personal micros are 8-bit machines. The CPU then sends bytes of our program one at a time to part of the computer's memory. Well, this is a representation of it. There's a byte of memory. Each of these has an address so that the CPU can find information that it wants later on. The byte stream goes into the CPU, then the byte is transferred in parallel, one at a time, into memory. Just imagine if one of these bits gets in the wrong place, the chances of a program working is very, very slim. Now, this CPU can use about 64,000 bytes of memory at any one time, or in computer jargon, 64K. But only some of that is available to hold our program or information typed in from the keyboard. This is the working memory space of the computer. These chips hold 16K of working memory. That's over 16,000 bytes of information. And you can add more by plugging in more chips right here in front of me, up to a maximum of 32K. That enables you to handle bigger programs, more information, or better graphics on the screen. It's called random access memory, or RAM for short. And on this particular machine, it's volatile, which means that if you switch the machine off and you switch it on again, you lose all the information and the programs you've got in your memory at that time, and you've got to input them once again. Well, this isn't the only memory in the computer. You remember, this is an 8-bit machine, and it can have up to 64K of memory. Well, these chips over here also form part of the memory, but these contain programs which are permanently burnt into them. This one here contains instructions for the language which the computer understands, in this case, BASIC. And this one over here contains what's called the machine operating system. It's the program that does the housekeeping inside the computer itself, how the computer makes letters appear on the screen, and how it knows what key I'm pressing when I'm using the keyboard. Now, unlike a program held in RAM where the information is volatile, this kind of program doesn't disappear when the power's switched off. There's a representation of memory. If I switch the machine off, then on again, the exact same representation is there. It's what's known as read-only memory, or ROM for short. Well, over here, there's also some empty sockets where you can plug in chips which have a variety of other programs burnt onto them. For example, a word processing program, or even a different language like Pascal. Well, we've only had time to look at the most important chips in this micro. There are many others concerned with linking the machine with all kinds of different input-output devices from the outside world. Now, let's see how I get out of here. How about that? Well, we've seen some of the things you can attach to the computer, and here are a few others which we'll be looking at in the course of the series. Now, in a similar way to the way we stored our script and then printed it out on a printer, so we can store a design in the memory of the computer. And here we've got a design of a house in the memory of a computer, and we're rotating it around almost as if we're circling the house in a helicopter. It would be possible to change either the program or the data to change this if you didn't like a particular view. Now, if we wanted to print that out, a normal printer really would be rather unsatisfactory. So we use this device, which is a two-dimensional plotter. We can hit the key and away it goes. Now, it prints it with a pen there of one colour. It's a black pen that we happen to have in at the moment. At the side, there are other pens, red, green, and blue, and so on. And it can interchange those pens to give a sort of multicolour effect on this line plot. And it's quite a high quality. The plot is an expensive piece of gear. It plugs straight into the computer at the back, and there's a special software to drive it. Well, here's a more modest setup which makes use of yet further connections to the machine, opens up another avenue of interest. What's happening is my voice is being picked up by the microphone, fed through some electronic gadgetry, and then the computer analyzes it and feeds it back here. We get this trace here, and the man even opens his mouth. Ha, ha, ha. We have another device here which can also input information into the computer, and I'll read another program in from disk, and there we have a representation of a weighing machine, and on the side the same information displayed digitally. All I have to do is to press this pad. You are 31 pounds, it reads it off there, and on the weighing machine it moves. Not only can it do that, but it can actually weigh me. I simply have to print on this. Of course, it's rather a cheap piece of gear, this, and it's very inaccurate, but it'll give some representation of what you are 205 pounds. Not only will it read it out digitally, but I simply press a button, and with a bit of luck,
You are 205 pounds.
and need to lose some weight. Well, in later programs, we'll look in more detail at how we can use it for displaying graphics, making music, controlling equipment, and handling words. Well, amongst many other things, we'll be talking to the computer and getting it to talk to us, and looking at how it can monitor what's happening in the world around it. Next time, we start looking at how you can write your own programs. Until then, goodbye.